Assalamu alaikum. Welcome to the last lecture of the series on advanced computer architecture. Today we are going to have a recap and a review what we have learned in this particular course. Now, we started with certain assumptions. We assumed that the students who are registered for this course have gone through the course on digital logic. They have also learned the assembly language programming. With these assumptions, we did not stress through this course on the aspects of assembly language programming. Though we did work out certain examples, and we also provided an assembler and simulator to work with the examples given in the course. Nevertheless, the stress was not to have a digital logic review or to practice the assembly language programming. However, we wanted to have very strong concepts of the computer architecture. First of all, we started with the concepts of computer organization. Now, basically, you might have just well understood that computer is a sequential machine. Now, it is based on the concept of von Neumann, and we just said that under the stored control program, we have an interconnection of three fundamental components. So, in any computer, we would have a CPU, we would have a memory, and an I/O. All these three submodules are interconnected with a shared bus. This shared bus has got three different parts: the address bus, the data bus, and the control bus. Under the control signals, the corresponding address is communicated on the data bus, and the data from the CPU to the memory or to the I/O is transferred. Now, to have a very well organized picture of the computer, the concept is that of a stored program, and that is based on fetch and execute. That was the starting point. We assumed that in a given memory, from a given starting address, we have both instructions as well as data. Now, the CPU would fetch a particular instruction, execute it, and then fetch the next instruction. Now, we just looked into the functionalities of a course on computer architecture. We said that there are different views that an architect could have. We wanted to have certain abstraction. Now, you could imagine that an architect should be able to design a computer. Nevertheless, there is no shortcut to experience, and the idea for this course was to give you the tools and the fundamental concepts. At the end of the course, of course, you will not be able to design a complete computer, but still you would know that how different architects have designed computers in the past. And based on that, you could better understand the functionalities of the computer. Now, von Neumann said that we have one common memory both for data as well as for the instructions. So, instructions as well as data is fetched from the same memory. And this is the internal bus which we are talking about, which interconnects the different parts of computer, which we have said the memory, CPU, and I/O. Now, after going through the organization of the computer and learning the concept of fetch and execute, we said that one instruction is fetched at a time, then it is executed, and then this sequence goes on and on from one instruction to the other instruction. Now, the architect would look at different points of view. The CPU is the main thrust for an architect. What is within CPU? We said that the taxonomy which we followed was there could be different design aspects. We discussed three important aspects. We said we could have a CPU which is based on accumulator. So accumulator based architecture means that we have just a register where we have one of the operands, the second operand comes from, for example, from the memory, and the result is again placed in the accumulator. So the limited number of registers are there. It's not only the accumulator, but the status of the overall computer would be determined by other registers like program counter, which keeps a track of the address which is being fetched, and then an instruction register and possibly some of the status registers to indicate the status of different bits like overflow and so on. In the taxonomy, we also discussed the second example of a stack-based strategy. In the stack, we say that we could organize a group of registers or a part of the memory as a last in, first out, and we had options of push and pop. Then we discussed in more detail the general purpose register architecture. In the general purpose register architecture, we said that there are a number of registers. Depending upon the architect, he could define the width of each register. For example, each register could be 32-bit wide or 16-bit wide, depending upon the choice of the architect. We also discussed the very important concepts of what is called the instruction set architecture. The instruction set architecture gives us a programmer's view, and it is a tool for the programmer, so the programmer has the available resources. We say that the resources available to the programmer are the CPU or the registers corresponding to CPU. For example, if we have a general purpose register architecture, then a number of registers along with the program counter, the instruction register, and then the memory map. Depending upon the width of the address bus, the corresponding space in the memory or addressable space would be dictated. As an example, if we have 32-bit wide address bus, then the addresses would be positive numbers starting from 0 up to 2 raised to power 32 minus 1. So the programmer would have available the memory locations from, in this example, 0 to 2 raised to power 32 minus 1, plus the registers which could be designated as RA, RB, or we could say R0 up to R7 if 8 registers are available, PC for program counter, and IR for the instruction register. We also discussed two important concepts, and we said that the architects could design the instructions which could be fixed or which could be variable as far as the size is concerned. Now, these lead to the RISC and CISC architectures. The RISC was a reduced set instruction set architecture, and CISC is the complex instruction set computer. Now, in the case of a CISC, we have different instructions varying in width. One could be, for example, just 1 byte, another one could be 2 bytes, or another one could still be 4 bytes. Whereas usually in the case of RISC machines, all the instructions have got same width, or the number of bits per instruction is the same. Now, why do we prefer to use RISC? Is that in a given clock time, and which is gradually decreasing. When we increase the clock frequency, the clock time would decrease, and the instructions should be such that we could complete it within one clock cycle. Now, that gives a simplicity in the case of RISC. Whereas in the case of CISC, the instructions could be more complex and may not be computed or executed in one clock cycle. Now, both the strategies are practically available, the CISC and RISC, but we laid more emphasis and went into more details of the examples for RISC. We discussed the different instructions which are available. Basically, we defined different 4 classes of instructions. We could have instructions as arithmetic instructions, as logic instructions. We could have the shift instructions and then the jump instructions. Now, all these instructions, which instructions to opt for, that would be the job of an architect. For example, an architect may opt only for add and subtract, and then through software implement multiply and divide instructions. Similarly, the jump instructions may be different, jump on 0, jump on not 0, and so on. A variety of the instructions could be formulated, and therefore the different parts of the instructions would define the execution, how this instruction would be executed. So in machine code, a part of the instruction would give us an opcode, and it would define what operation is to be done. And usually, instead of writing in the form of machine language, which is laborious and tedious, we said that usually we'll write in the form of assembly. And hand assembly is again really difficult. So to convert assembly into machine, it is an automatic process, and an assembler, which is a program, could be used. So the assembler would automatically convert the program which is written in assembly of that particular processor. So therefore, an architect, when he defines the instructions for each instruction, he would define the opcode, and rest of the instruction, different parts of the instruction, would tell where are the different operands for that particular instruction, and then we could store the result at some place. This information would be contained in the instructions. So as a result, whenever we have a processor, an architect has designed a processor, he would make available to the user, that is a programmer. By default, we assume that programmer is an assembly language programmer. So he has access to the instruction set. Each instruction is explained, and the method is given how to fetch the operands, and then where to place the result, how to store the result. All these details depend on a particular processor. To give really a good feeling of the things going through, for explaining the instruction set architecture, we went through the example processor. In the textbook, a processor which is called SRC, or a simple RISC computer, that was taken as an example. On top of that, there was another processor which we discussed, and we just called it a Falcon processor. In the case of Falcon processor, we also provided you the simulator along with the assembler, and we had one lecture purely to illustrate the different features of the assembler and the simulator. And this is just a tool which is provided to work with different instructions given in example programs, and that just gives you a handy tool. Instead of going into laborious hand assembly, you could use this assembler, and then through simulator you could watch the contents of different registers, you could watch the contents of different memory locations, and also the status registers like program counter, and then each instruction would be illustrated, and you would have really a good concept of the execution of a particular program in assembly. And through this simulator, you see the machine code and corresponding contents of different registers as well as the memory locations. Now, as we said in the case of a RISC processor, the length of each instruction is the same. We also discussed some variants apart from these two processors and just emphasized some of the important concepts. We had laid certain stress just to illustrate that how an instruction set architecture works, or how different instructions could be used by designer or an architect of a particular processor. And I hope with this idea of instruction set architecture, you need to work, and you might have worked through ISA and got really a feeling that what an architect could correspondingly provide. We also went into the details of the CPU design. And in the CPU design, along with the instruction set architecture, we also saw how the performance could be improved. The performance could be improved by increasing the clock frequency. Naturally, the clock frequency, when it is higher, the throughput would be higher, the execution would be faster. And to what extent this clock frequency could be increased, that depends on the technology available. Now, earlier we could have 100 megahertz clock, and at present we could have even 2 gigahertz clock at this time. So that's the technology layer that works with the corresponding availability of logic, or you could say the latest tools. At present, if an architect would design, for example, a chip, he has got availability of very high level languages like Verilog, and could design through that particular tool the application specific integrated circuits. And CPU is also, for example, one of the chips, and this chip could be just manufactured by the corresponding manufacturer. However, we have just hidden these details, and we said that we will work only on the top level, that is the system design level. At the lower level, you could have the logic design level, or below that the mask level could also be looked into, and the people who are working in fabrication, they would then just dictate and define the corresponding masks and the manufacturing processes. Now, in the CPU design, we went through a very nice and a simple exercise, and we said that we need to have certain abstraction. And we defined the notations, or we just called it a language, and that was the RTL, and we said the register transfer language. In your textbook, we said it is just defined as RTN. Now, we need to know the static behavior as well as the dynamic behavior of the processor. So when any particular instruction is executed by using a particular CPU, then the data would be transferred from one register to another, from register to the memory, from memory to the register, and then we need to know how this data transfer takes place, right? And therefore, we just defined it in the form of what we called the behavioral RTL and then the structural RTL. The behavioral RTL defines what is to be done when an instruction is to be executed, and structural RTL defines how it is done, right? In the form of logic implementation also, we could see the details. We illustrated the use of RTL through the fetch execute instructions. And at this point of time, I don't want to go again into the details, but we just want to see the concepts that we have learnt. We also discussed quite in detail the different addressing modes which are available to the architect or to the designer of a particular CPU. Now, you remember immediate mode, for example, takes the operands right from the same instruction. It may be available in the form of a data or an address, or correspondingly the immediate mode usually defines the operand as a part of the instruction. We also discussed the register relative addressing modes and the memory relative addressing modes, the base or indexed addressing modes. Which addressing modes are to be used would depend on the architect. Usually in the RISC architecture, the addressing modes are relatively limited, and in the case of CISC, the addressability is wider. More modes are available for CISC machines than in the case of a RISC machine. Now, we also went into the details of the CPU, and within CPU the data path. We said that how do we implement the data path. In the CPU we had two parts. You could say that registers, along with these registers, the arithmetic functions or shift functions are implemented by a combinational circuit. And we also discussed at a later stage the arithmetic logic shift unit, and we said that the operand come into the ALSU, and as an output it goes back to the bus. However, the data path comes from the data bus. The operand comes through data bus to the input of ALSU, and it goes back, the result goes back to the data bus. We need to synchronize these activities, and we looked into three different options of the data path within the CPU. We saw the simplest implementation in the form of a unibus. That means only one bus was available, and as a result, we needed to have buffers or some intermediate registers where we could store temporarily the data obtained from the bus or as an output of the ALSU, and then feed it back to the data bus. So three different implementations were discussed, that is the unibus or two bus or three bus. Gradually, as we go on from unibus to two buses or three bus implementation, the corresponding logic would increase. We need to have more tri-state buffers. Now, whenever we are using a particular bus, we discussed the idea of bus contention. Now, the bus contention means that at one time the bus could be driven from only one device, from one output. If two devices try to drive the bus simultaneously, then invalid data would be available, and that is a situation what is called bus contention. In order to avoid bus contention, we have the tri-state buffers as an example, and these are activated only under the control signals. Now, these control signals could be generated either by using combinational circuits, that is the logic circuits, which could be hardwired, or it could be controlled through a microcode. In order to have synchronization from the main clock, from the master clock, we need to generate individual clocks or the steps corresponding to different timing sequences. So a sequence of timing, which we just could call T0 to T8, for example, could be generated using a counter or through a microcode. Now, all these activities need to be coordinated, and an appropriate control signal is to be provided, and that's the objective, and an architect must ensure that that would be done by proper design of the control unit, which is a part of the CPU, right? Now, for the CPU, if we have just one instruction being fetched and then executed, the throughput is relatively low. How could we increase the throughput? That could be done in a variety of ways. One of the simple concepts that we discussed was that of a pipeline. We say that the different phases or different activities could be defined, and within the same clock period, these activities could be done simultaneously. We discussed the analogy of just a production line, and we said on similar pattern we could define the pipeline for a CPU. Through the pipeline, we have the execution in different phases. Different instructions are simultaneously executed, and that gives a better throughput. As an example, if we have one instruction which needs to fetch data from the memory and it would take some time, simultaneously the next instruction would come into the pipeline, and in the pipeline we could have simultaneously 5 instructions at different stages of execution. So again, the idea at this time is not to explain again what pipeline is. We have discussed that in detail. Through the pipeline concept, the throughput is increased, and therefore the average performance would increase for the CPU. Now, an architect has the option to have a VLIW, a very large instruction word, and increase the throughput, or he could use the concept of a superscalar. In the case of superscalar, the architect can provide more than one unit. For example, the floating point unit could be more than one. Similarly, the integer operation could be done simultaneously, and the branch instructions could also be manipulated simultaneously, concurrently. So the idea is that instead of fetching just one instruction at a time, a number of instructions are fetched, pre-fetched, processed, decision is made. If it is a branch instruction, for example, then actually branching would take place later, and through the process the speculative branching decision would be taken, and therefore the throughput would increase. So the difference between the pipelining and the corresponding prescaler would be that in the case of a pipeline, one instruction would be fetched into and pushed into the pipeline, right? Whereas in the case of the prescalar architecture, we have fetching or prefetching of more than one instruction, and therefore more than one logic unit would be available. ALSU, for example, would be more than one. Similarly, the branching decision would be simultaneously taken, and at the end, some of these decisions might be discarded, but still it would increase the corresponding throughput. Through these advanced techniques, we were able to improve the throughput. How to measure the throughput? For that case, we said that the bottom line is the execution time for the CPU, which depends in turn on the number of instructions, then the number of clocks per instruction, and the clock time. Now, this is just a reference. However, to check the actual performance, we need to have certain benchmark programs, and these benchmark programs are provided by different organizations, and we have programs like Whetstone, Drystone, and Spec. Now, it provides a combination of different instructions used in a particular program so that an average throughput or an average performance is given in terms of the execution time for a given particular program. So if you have two different CPUs, two different processors, same program is run on these two processors, and the one which requires lesser time would have a better performance in that case. So these benchmark programs are important for an architect to check the throughput in a given CPU. After discussing the design of CPU, the second important subsystem that we talked about was the I/O, the input-output devices. Now we said that these I/O devices are peculiar in the sense that some of these devices are very slow, others are fast. Examples, we might have an input from a keyboard, an output to a printer, and then we said the disk would also be considered as an I/O device. And this was an important point which we emphasized, and we said that the I/O is organized in such a way that we have communication from an I/O controller in the form of a block. So we are not having one-to-one address correspondence as we had in the case of a memory. The memory was organized, just we send an address on the address line, corresponding data is available on the data line under the control of signals on the control line. This is not the case for the I/O devices. Now the I/O devices need to be synchronized in such a way that a variable speed is accommodated, or we have a diversity of different devices. We also looked into some details of typical device, that is hard disk. We didn't touch upon other peripheral devices. Through these peripheral devices and an appropriate I/O scheme, we spent quite a lot of time on the concept of I/O interface. 3 techniques were discussed in detail. We said that the simplest technique is a programmed I/O. The programmed I/O simply just goes through this concept of simple polling. That is, the CPU would scan and cyclically go through different I/O devices and check if it is ready or if it has got some activity or some interaction needs to be done. So the programmed I/O is very simple to implement. Nevertheless, its efficiency is pretty low. The second aspect that we discussed was an interrupt-driven I/O. In the case of interrupt-driven I/O, we said that when an I/O device wants to communicate or it has got some data transfer activity, then it would initiate an interrupt. This interrupt would be communicated to the CPU, and then CPU in turn would recognize and find out which particular device wants to communicate or send data. It would enable that particular device, and then the data would be transferred. And this is the interrupt-driven I/O. Now, in the case of interrupt-driven I/O, though the efficiency improves, it is better than the programmed I/O. Nevertheless, there is a problem. The problem is that all the data goes through the bus of the CPU, and the bus of CPU, and therefore the CPU cannot take any other activity during that particular time. So, therefore, in order to reduce the burden on the CPU from the I/O device, we could have a third option, and that is DMA, or direct memory access. In the case of DMA, the control is given from CPU to a DMA controller, and under DMA controller, the I/O could communicate directly to the memory. So therefore, the data transfer could take place between I/O device and the memory. For that point of time, the CPU would be free. So the burden on CPU would reduce, and when bulk of data is to be transferred, then DMA technique is pretty efficient. Finally, we also discussed that if we could make the I/O controllers more intelligent, we could put the processor, a new processor, into the I/O controller, and that could overtake the burden from CPU and make certain decisions of looking at and providing the acknowledge or looking at the interrupt or DMA functions. Then these I/O controllers would give better performance. We also looked into the performance of these I/O devices. The performance of these I/O devices, apart from the performance like CPU, we just said that it would also depend on the queuing functions. There would be a queue in between and some waiting would be involved. Since there are many I/O devices connected together, there is a capacity which could be, for example, a number of hard disks are simultaneously trying to access the memory. In such a situation, we have a parameter which corresponds to latency and throughput. So an architect needs to look into these parameters and optimize the system in such a way that concurrently more number of I/O devices could interact, and then queue is as short as possible, the throughput is as large as possible, and for testing the I/O performance also we looked into the fact that there are certain benchmark programs, and these are becoming increasingly important for online transactions, and therefore the real-time scenario would be that I/O activity is gradually increasing, and therefore having a less burden on the CPU would mean a better overall performance of the system. For these I/O subsystems, we also discussed some examples with our reference processors. We also discussed the memory mapped and non-memory mapped I/Os. And we went into some simple assembly language program for all the different techniques of programmed I/O, interrupt-driven I/O. We discussed the input device as well as examples of output device. Now, after discussing the I/O, we went to the third component of the overall computer system, and that is the memory subsystem. The memory subsystem is as important as the CPU itself, because the overall performance would heavily depend on the intercommunication between CPU and the memory. Now, we just discussed the different implementations of the memory itself. We discussed the static RAM, and we also discussed the dynamic RAM. Now, we looked into how to implement a memory cell and then expand the rows and columns to make a complete memory bank. Now, we said that the static RAM has got less access time but is usually more expensive. Now, it doesn't lose the data, and therefore no refreshing is required. Whereas in the case of dynamic RAM, we need to refresh, and this would in turn would be dictated by the manufacturer that how quickly we need to refresh. Now, once we obtain a particular memory bank, whether it is in the form of SRAM or DRAM, the communication or the interface with the CPU is through some buffer registers. We discussed examples of these buffer registers in the form of the address register or memory address register and the memory data registers. So the communication to and fro from CPU to memory and memory to CPU would take place through the instructions load and store, or it could be, if it is a memory mapped, then load and store, and if it is a non-memory mapped, in and out instructions could be available depending upon which particular processor do we use. Now, one important feature of designing a memory subsystem is that the architect tries to provide theoretically infinite resources of memory to the programmer. That means there should be no limitation to the programmer that he is pressed by memory, that his memory is not able to store the program. We discussed the strategy of building a hierarchy in the memory subsystems. Now, we said that the nearest to the CPU, the memory, would be fastest, However, it would be more expensive. And as we go away from the CPU, we have a cheaper memory. Now, the disks, and in the form of disk arrays, we discussed with reference to the peripheral devices, we provide a bulk memory. Then main memory is usually provided by DRAM. And then we have a part of the memory in the form of cache given by SRAM. So building from the bottom, which is the virtual memory, you could say, it is managed in the form of pages, and then we go up to the main memory, then to the cache, and to the registers within the CPU. Through an appropriate strategy, we just build this hierarchy, and managing this hierarchy is important to achieve two objectives. Number one, that is to provide almost infinite resources, that means as much memory as possible. And secondly, the access time should be as low as possible. To reduce the access time, we use the concept of cache nearest to the CPU and the virtual memory for managing the disks. So therefore, using the principle of locality, we said that if we use one particular data, then probability of using data next to it or in the addresses very close to it is higher. The probability is higher. So therefore, instead of moving just one byte or one word, we transfer a block of data. And how this is managed, all these details we discussed thoroughly in the memory subsystems. So therefore, the memory subsystems are extremely important to increase the throughput and to have an overall better performance of the system. Now, I/O together with the memory subsystems connected with the CPU would be coordinated and would provide an overall computer system. Now, when we have just one computer, one CPU, then the performance would ultimately be limited by the clock or by the architecture that we have. We just said that through parallelism or through instruction level parallelism, we increase the throughput. But nevertheless, there is a limit. How to increase the throughput further? We discussed techniques. We went into the principles of networking and computer clusters. Now we could say that, well, a number of CPUs could be provided, a number of memory subsystems could be provided together, a number of IOs could be coordinated. There could be different ways of interconnection. However, we discussed that the performance may not increase linearly, right? We expect that if we have 10 processors, the throughput should increase tenfold. This might not happen. It might happen for low number of CPUs, but for very large number of CPUs, the throughput may not increase. It may saturate. It is just like having committee or group of people. When there are 2-3 people, the coordination may be very good. However, if we have a committee of 100 people, then the result may be adversely affected. Same way, the intercommunication of different CPUs, that would affect the overall performance. We looked into the interconnection. The interconnection possibilities could be that different CPUs, they share one common memory, right? Or we could have independent memories provided to each CPU, and these could be connected either in the form of, let us having a switch, or it could be connected through a shared bus, which could be a local area network, or we could have even a wide area network with remote resources coordinating with each other with a message passing technique from one to the other. So therefore, the computer networks are becoming increasingly important, and a computer architect should know about these ideas and implementation of the computer networks. The concepts learned in the networks may also be used locally or within a particular processor as well, or in the subsystem. Now, as we said that if we have just a shared bus, there would be a limit to the throughput. So within the chip itself, the concept of using a switch instead of a bus is becoming increasingly popular, and the overall bandwidth could be increased, or throughput in terms of megabytes per second could be increased in this way by having a concept of switch instead of just a shared bus. The concept of bus versus network is really important. Now just imagine that if we increase the number of processors, and we have two options. One is to use a shared bus, the other one is to use a network. So we just plot on the vertical axis three different parameters, right? On x-axis, we increase the number of processors starting from 1 up to, let us say, 100 and onwards. On vertical axis, we plot on one side the cost, then secondly the performance, and the third parameter per unit performance per unit processor, right? So if we have a network, all these three, the first two would increase linearly, and therefore the cost per unit would be almost just a straight line, a horizontal straight line. Whereas if we consider the bus as an example, from 1 up to, let us say, 10, the cost would increase linearly, right? The corresponding performance would increase linearly. However, after some number, the performance would decrease, and therefore we would just have a window, just as an example, from 1 to 10, the performance increases, then it stays constant from 10 to, let us say, 30, and after 30, it comes back, it comes down. So therefore, a better option would be to use distributed processing. The processors be located at different places, but they coordinate with each other. And it would be a model of independent memory for each CPU, and the results would be passed on from one computer to another computer. And this concept is used in computer grids and also to form the computer clusters. Now we finally also discussed another important aspect, and that is of error control. Now, as long as we remain within the CPU, within the chip, the errors are less, and we say that it is a protected environment and corresponding error rate is low, or bit error rate is pretty low. However, whenever we have a communication with the I/O devices like disk, from disk the data is to be read. There is a mechanical movement, and then the controller for the disk needs to have certain mechanism for error control. We discussed the detection of error and then correction of error. We said there are two techniques. In one case, we just find out the error, report it back to CPU or the controller. The controller can repeat that process and resend that message or resend that block of data where the error occurred. And secondly, it could also correct. However, the correction of errors would require larger overheads. We discussed Hamming code as an example. The simplest was parity code just for detection, then Hamming code, and then the CRC we discussed, and that forms a part of the packet, and this control, error control, is also a part of the overall network data transfer. When data is transferred from one point to another point, it's extremely important to ensure the integrity of data and the correctness of data, so the error rate should be as low as possible, and that would be designed and reported by the overall supervisory system, and the software process could not be undermined. So if we are talking of just one processor, the operating system would take care of these aspects, and if we are talking of a network, then the network management system would take care of these aspects of the error control. With all these ideas put together, there is a simple and important question. Is computer architecture evolutionary or revolutionary, right? Now, day by day, new concepts are coming up. To start with, it was an evolutionary process. The starting point in computer architecture was the concept given by von Neumann, that is, the stored program concept. We had the same memory both for instruction as well as for data, and therefore the fetch execute concept was there. Now then later on, to increase the throughput, we went to the concepts of pipelining or superscalar, or that means in that case the architecture went on to have parallelism in the instruction. Now the memory for data and instruction was also isolated, and we could have a better throughput through segregation of data memory and the instruction memory. Till that point of time, it was an evolution. The revolution started with the networking and the multi-processing. That means a number of processors being used. In that case, the throughput increased manifold, and we could have message passing and coordination of different processors along with the corresponding memory processing the data, and that trend is going on, and we are presently having applications with the computer clusters and computer grids. Now at the end of this course, I would suggest that if you have any feedback about the course, please do correspond. You are free to communicate with Dr. Anjum and our team and get as much support as you want regarding all the tools available, or class notes are available, and any sort of communication would be appreciated, and the feedback would also be appreciated. For this course, that's all what we want to talk about, and Allah Hafiz.